So here is a porism or quasi-porism where I have an outer circle of radius 1, this black circle, and two nested caustics that in this case are concentric. So the green circle and the red circle are concentric, and I'm going to be doing a Poncelet transverse, a variant of the Poncelet transverse, where I'm actually switching between caustics in round robin fashion. So I'm going to do 6 iterations, and I've set things up here. I found this configuration manually in such a way that after 6 configurations, I approximately go back to P1. You can see here that the Euclidean distance squared is something like 6 to the 10 to the minus 7. So it's pretty small, meaning that if I took the square root of this, it would be like 1,000th of unity, and unity refers to the circumradius, the radius of the black circle. Now, what's surprising about this is that if I rotate P1 around the circle, I pretty much preserve this very small distance between the first and 7th vertex of this polyline. And as it's obvious from this figure, from this animation, these 3 circles are not in the same pencil as would be required for standard Poncelet porism. Okay, so the question here that I'm asking is, why is it that for this particular configuration I can keep the error bounded to say within 1,000th or 1/10,000th with further optimizations of the circumradius? So I have a few other examples here. Let's look at another family, an n equals 8 that I've set up. Again, n equals 8, right? So here we go. This is the one I want to animate. So here's an n equals 8 family that is keeping the error pretty bounded. Okay, and again I have 2 caustics. In this case here, the centers are collinear of green and red, but they're no longer concentric. Okay, again found manually. Let's look at another example here of n equals 8. Again I have 2 caustics, red and green. Their centers are collinear with the center of the circumradius. But red and green are not concentric. I got a different kind of n equals 8. I'm also alternating. I'm picking these caustics in round robin fashion. So I'm getting the same phenomenon of very small bounded error. I want to say that this is very rare. Just closing a circuit does not guarantee that you're going to stay quasi-poristic, as we have shown in previous videos. Let's see if I have more examples here. I have an n equals 10 porism, a quasi-porism. Let's hit the right button here. Is n equals 10, also maintaining the error pretty bounded. So if you look at P1 over here, right, if you investigate what's going on with P1, I want to know if the 11th vertex and the first vertex are more or less co-located. And instead of doing this visual, I'm actually just showing what the Euclidean distance squared is between these two. So again, it's staying pretty bounded. It oscillates in this case here between 10 to the minus 6, 10 to the minus 7. I can further optimize this if I actually manually went to try to do it. What else do I have? I have another n equals 10 here. Oops, I'm doing the wrong thing here. I have to hit this button. Again, I have another n equals 10. Again, collinear caustic centers, and now they have the same radius. Okay, so it seems like collinearity of the centers or concentric, the 2 centers of the caustics being the same, seems to help this phenomenon. Okay, if I actually just try something generic, it's harder. Although I'm going to show you guys a counterexample. Here's n equals 8 non-collinear. So the 3 centers, the black, red, and green, are non-collinear, and I'm getting a 10 equals 8, whose error is also staying pretty bounded. So it's not entirely the case that collinearity is required. There seem to be minima of these sort of max errors over, let's count the number of dimensions, right? I have 2 dimensions for the translation of the red center with respect to the center one, the black one, and I have another 2 of the green with respect to the black one. So there's 4 dimensions there. And now I have the 2 radii, which are independent. So this is a 6-dimensional space, and all we're saying is that there's some corners of the space where you can actually minimize the max error over over all positions of P1. Now, what is the theory behind it? What is the approximation? What are the, there seems to be an inequality that is getting preserved here, right? So, again, we don't always need symmetry, as is illustrated here. Let's see, do I have more examples? I have an n equals 18. And if I'm talking about n equals 18, I want to know that the 19th vertex, which is emanating from this 18th vertex to this green guy here all the way to P1, I want to know that the distance between P19 and P1 is a small number over all values of P1. So just to give you guys a final example why this is not always guaranteed, let's look at the first two that I had here. I have an n equals 4 that is not closed. And so what's happening here, right? This is not closed. So I can rotate these guys. Here's my P1. And I can investigate if this P1 ever comes close to my P5, which it doesn't, right? So now I can actually vary, for example, this radius like that, and I can investigate now that if over the entire rotation there is some luck here and there isn't, so let's go ahead now and play with the other radius, this one over here. Looks like we're going the right direction. Let's move the center around. Let's place it here. Doesn't seem to be helping. What if I go downwards with it? Doesn't seem to, it barely moves P5. You can see P5 is mostly stable with respect to, P5 is over here, right? Up and down motions of this guy. And left and right also does not make any significant progress there. What if I now make X2 move, going in the wrong direction? This has a sort of a Poncelet closure flavor in that there are directions that will get you closer to the Cayley condition or the closure situation, others which will not. So you can pretty much judge by looking, for example, at the distance between P5 and P1. Namely, I'm trying to figure out if there is a particular choice here that would bring me as close as possible. And yeah, of course I cannot make this radius be bigger than the black radius, at least in this implementation, right? And it looks like I can't, right? If I actually rotate this whole thing around and I try to see if they ever meet, they never meet, right? So this is truly a sort of unexplored kind of phenomenon. Perhaps if I go this way here, yeah, if I now move this guy that way, and then, no, not this way, you want to go that way, and then this guy here, yeah, this is helping. This is helping. You can see there that this is helping. So I want to go this way, and I want to go up a bit, like that. So I think I'm going to hit the closure there, and just searching for it manually, right? Yeah, so I'm pretty close. You can see that I'm already pretty close to closure. My error is coming down, so now I'm going to do this manual binary search until, yeah, I'm hitting an error of 10 to the minus 5 here, squared, right? 2, 3, 4, 5. Yes, and I can probably do some further optimization. Now I'm 10 to the minus 6. I can play with these decimals here, and I can probably get this guy to go to 10 to the minus 7 or 10 to the minus 6. But here's the crucial part. We've closed in n equals 4. Is this thing going to remain closed as I now move P1 across the outer circle? And none of them do remain closed, okay? None of the examples I showed you guys before, you got perfect closure. But you can see here that the deviation here is of the order of, let's call this 10 to the minus 2 or 10 to the minus 1 even, error square. So when you take the square root, this is going to be of the order, take the square root of that. This is going to be something like 0.1. It's 1/10 of the circumradius. Okay, so the current error there. And there are points where I'm actually going to go through P1 right here. So there are these sort of roots, error roots, where I actually go through P1 and then I deviate again. Okay, so it is curious that some configurations have unstable and pretty large error compared to the circumradius of the black circle, and other configurations like n equals 6, for example. Here I have two concentric circles. My error is 10 to the minus 6. I can probably further optimize that. Okay, I'm sure I can play around with some of these settings, and perhaps not this one. Yeah, this one he doesn't want to do it. Yeah, he doesn't want to do this one either. Let's go ahead and put it back on where I was, this one over here. And then, so now it's, yeah, Let's try to do it again. Yeah, so go back to that 10 equals 6, n equals 6. So in this configuration here, which we started the video with, you can see that 10 to the minus 6, right? So the question is, there is some mounting experimental evidence that suggests that in the 6-dimensional space of a fixed outer circle and two sort of arbitrary nested circles, they don't have to be nested within themselves. Let's just pick the case where I'm actually doing round-robin execution of these tangents, right? What are the pseudo or the sort of this let's call it that way, these pseudo-Cayley conditions, okay, that will keep the error bounded for all values of P1 over the outer circle. So why is it that this configuration here presents amazing stability and other ones do not? All right. Thanks for watching. I'll see you in the next video.